Right. Guess we'll get started. This is discussion 15. And today we don't have a handout. We're going to work with um, a brief review of what we have done in the class. This is like also happens to be the final class of, the final discussion of this semester. I hope you enjoyed and you learned in the process. We'll just go over some of the concepts in a general sense, just to give you an idea as to what really have we covered in the class, and if we come across any problem, how you're going to tackle it. Before we do that, let me get one important thing which we need to do. That's going to be our course evaluations. So you will have received an email from cevals@usc.edu asking you to do your course evaluations. So as last time we did it in an unofficial way by using a Google form. But this time, this is university. This is mandated by university, but it's also managed by university. We take all our comments very seriously. So I'll give you around 5 to 6 minutes over this call. Just search for email in your email from cvals@usc.edu. And I would really request you to turn your any comments that you have about the class. I'm talking about the discussion section specifically. Anything that you enjoyed, any areas that you think can potentially be improved. I'm also supposed to uh, kind of read this out. Um, so I'm going to just read this out. Bear with me. So learning experience evaluations are your opportunity to provide feedback to your instructor. USC and its faculty take these evaluations very seriously, as they provide valuable information that faculty and schools can use to improve teaching. It is important to remember that the learning process is collaborative and requires significant effort from the instructor, individual students, and the class as a whole. Please provide a thoughtful assessment of your experience as well as your own effort, with comments focused on specific aspects of instruction or the course. Comments on personal characteristics of the instructor are not appropriate and will not be considered. Evaluations should be completely completed individually with no undue influence by either a student or instructor. Should any inappropriate behavior occur, it should be reported to the Office of Institutional Research. Okay, so just in case people who joined in late, we are going to work with our course evaluations first of all, and then I'm going to walk you through a brief review of what we have done in the class overall. Okay, so just to make this is the first time I'm doing a course evaluation like this, but just to ensure that I don't speak and you don't see me, I'm going to switch off my video for the time being, and I'll get back to you in 6 minutes or 7 minutes. Okay, so we'll meet at 1:10 my time. I'm still around. I'm going to mute myself. Okay. So we had some 10 people respond out of 25. So if you have not responded, would strongly encourage you to do so. It's also your time to really pay forward in some sense. If we have done a mistake, and we're not told what mistake we did, we'll never realize, right? So it's just like how the comments on your homeworks and quizzes and exams work. So if I don't give you a comment, you'll never realize what mistake you did. Okay, so just in case you've not done so, these window will remain open till I believe 3rd of May. Sorry, 4th of May, 5th of May. Okay, so if you've not done so, please find some time and make sure you give your comments. Again, anything that you didn't like, anything that you think should be changed in the overall organization, I'm more than happy to make changes. This also was supposed to be my last semester teaching. I just defended last week. So, but I'll still have one more summer when I'll be teaching this course, the discussion section. So there is still chance for me to make changes and update anything that you didn't like about the course. Okay, all right. So the discussion will carry forward, and I'm going to, so what I did right now is I uploaded a review sheet. So it's not like a review sheet of questions. It's a review sheet of the concepts. First, let me stop sharing, and I need to share it again. Okay. Okay. All right. So what we are going to do today is I'm going to just walk you through some of the things that we have done in this class and kind of give you a progression about how to think about problems if you do them in the exams. Okay. So at this point, I don't think you require a lot of problems to practice. Most of you are pretty good with concepts, and solving any particular problem or anything to do with exams or anything in general will just require you to be familiar with concepts. Okay. So that's what I'm going to do. But before I get started, any questions about the any particular section that you would want me to cover, anything that's not as clear as other sections or anything that's not clear at all, any questions about projects? Project, not projects. Any questions about the project? Project is due tomorrow. And I believe this time most of you are at pace. But if you have any questions, you will still have access to my office hours tomorrow between 3 and 5. But I believe today would be a good time to start wrapping up your project and not wait till the last minute as usual. Okay, before I proceed, okay, we have something here. Okay, sure. Okay, so if you want to, so I'll stick around after the class as well. Those of you have questions about the R, about if you're getting an error in R, you can share your screen and you'll be able to show me what error you're getting so that I can help better. The tricky part about not being able to meet in person is if you just tell me that you're getting an error without telling me or without sending a screenshot, it's kind of difficult for me to figure out what would be the error. So sharing the screen helps if you're comfortable with it. Okay. Again, it's up to you. So I'll stick around after this class also, and you can ask me questions then if you have any questions that you would like to ask in person, or you can drop by my office hours tomorrow between 3 and 5. Any questions about any concept that you would like me to cover, particularly before I give you a general overview? We might be done in like 15-20 minutes. I don't expect it to be pretty long. It's just going to lay down the entire structure of what we did, so that will kind of help you to think about how to solve a problem. Okay, so I believe there are no particular areas that you would like me to cover, so I'll just get started. Okay, and since I'm going to look down, I'm going to switch off my video. Okay, so this course essentially, the way to think about this entire organization of this course is it's a lot of it's motivated by this idea of two-group testing. Right? That was if you consider what we did before midterm, that was essentially getting you in some sense ready for analyzing. Let me write this down in a much better way. So we started off with group testing. And the way we thought about group testing was, in the first scenario, we considered two groups. Okay. And what are these two groups and why are we interested in two groups at all? A lot of it is motivated by this fact that in a lot of clinical or in a lot of biological samples, you'll come across these two groups. One is a control, one is a treatment. Okay. And what is it that we are interested in? So that's called your null hypothesis. And most often or not, your null hypothesis is mu1 is not equal to mu2, and the alternate, sorry, mu1 is equal to mu2, and your alternate is mu1 is not equal to mu2. Okay, so this was our question of interest. Okay, so this is our question of interest. Now, in order to be able to really check this, before the midterm or before the first midterm, we learned a lot about what's a simple random sample, what does it really mean to be independent, and when can you consider independence between two groups. In order to be able to, let's talk about independence first. So a lot of these criteria are motivated by these facts. So let me write down a different number. Okay, so these were the two important concepts that you had to keep in mind when doing such kind of group testing, right? So each of these readings here and within the groups came from simple random sample. And if we are working with non-paired data, right? Independence implies that you're working with non-paired data, because if the data is paired, so let me make sure I make that clear. So this is right now not paired. Okay, because the moment you pair any observation, then this particular set of observations are no longer independent, right? They are dependent because they're being measured essentially on the same commodity or entity, whatever you want to call it. Okay, so how did we figure out independence? Well, that was covered slightly differently, and we covered this more in a probabilistic sense. And any two events are called independent if this holds, right? P probability of A, given that B has happened, is essentially equal to probability of A, right? So it's as good as uh, nothing has happened. Or alternatively, you can also write this as, okay. So probability that, so here the first interpretation is probability that A happened, given that B has happened, is not affected by the event that B happened, and hence it's equal to just probability of A happening, right? The second one is essentially probability of A and B happening. They're independent. So they essentially are equal to PA times PB. One universal fact that we also studied, and I think a lot of you sometimes get this wrong, is this fact. What is probability A or B, right? So this essentially means probability A happens or B happens. And this is not equal to this. And we saw why. We saw it in the essence of understanding these Venn diagrams. So this was, excuse me, this was A, this was B. Okay. So if I want to find out what's A plus B, I need this area. Okay. That's just A. This is just B. And this area in between is A and B. Okay. So what we have to do is we need to subtract this. Okay. So just one more, just one, if you have not been able to understand why do we subtract, That's essentially because this black area is what? So this is the entire probability that A happens. I'm only counting the black area, so I need to subtract the red area. So this is PA and P. This area is what? So we be consistent with the colors. This area is PB minus PA times B, okay? And if you add up, so this is the red area that I'm going to add up now because, yeah, so let me be consistent. And finally, that's your blue area, which is PB minus PA and B again, okay? So you subtract 2 times and this essentially leads up with this formula. Okay. So this formula essentially holds always. There is no restrictions. However, if A and B are independent, then you know what PA and B is, okay? One more formula that we learned universally that holds is conditionality. So conditionality or conditioning. So any two events, A and B, can be written in this form. Probability that A and B happens is the probability that A has happened given that B happens times the probability that B really happens. Okay. There's nothing special about A and B, so we can also write this in this format. Okay. Again, always holds. Okay. There's nothing special. With these two formulas, PA and B and PA or B is equal to PA plus PB minus PA and B, and this conditioning formula, you should in principle be able to solve any particular problem about which has to deal with probability. Okay. We also saw if you're given two if you're given two chain of events, we used to rely on probability trees. So I'm not going to walk you through example because most of you are now familiar with it. But let's say somebody is a smoker or a non-smoker, and we want to be able to calculate the probability that the smoker does, develops cancer, or let's say a test for what's the probability that the smoker develops cancer over all the other possibilities. Then we essentially used to do this branching operation. Okay, so the most complex problems in this case would just involve you to, which would just require you to draw a probability tree. Okay, most of you have already done this, and there is I've seen no particular errors arising from this particular example, so I'll just leave it that. Okay, so we'll not go into the details of the review there, but let me go back to what we originally started. Okay, so we digressed. So we digressed in the sense because this entire story of learning about probability, learning about independence, essentially helped us to kind of verify that what we are going to do with this two group samples is kind of satisfied. Now, when we were working in the two group samples, we had choices. Okay, so this is 1A. The first choice that we landed up was that the data was two group plus it was normal. Okay, both these groups essentially also allowed for normality. And then our choice of test was t-test. Okay, there was also one more sample where you also similarly had two groups which satisfied all these two criteria. So this is requirement. But this idea of normality or this concept of normality was not necessarily satisfied for this data. And for this, we relied on what? We relied on the Wilcoxon Mann-Whitney test. Okay. So again, we have come up with different test strategies, again, to be able to satisfy what we want to see in a two-group setting. In order to be able to understand or change this criteria, so right now we are working with two groups, which have our simple random samples and are independent among each other. If we change this criteria to have two groups but paired, well, this is one point where some of you get some of the ideas wrong. So first thing that you need to check is whether the data is paired. And let me be specific here. So this is not paired data. Okay. So any two group setting, the first thing that you need to be checked is whether the data is paired or not. The moment you decide that, you will be able to decide what value or what type of test would you be doing. So you'll have one more level to decide depending on whether the normality is satisfied or not. Okay. So if the normality is satisfied and it is not paired, so normality satisfied, you do a paired t-test. Okay. And the only difference between doing a paired t-test versus a normal t-test is what is the standard deviation that you use for the paired formula. Okay. Some of you do a mistake here. So make sure you will have access to all the formulas. The only thing that you need to figure out is what test you're going to do. Okay. So please don't do a mistake here. This is important. Some of you ended up using a wrong version of the t-test formula for midterm 2, and that just because so you need to explicitly write down what test you're going to do. And moment you write this down, you have access to all the formula. If you go to my review material, there's a table there which lists down all the criteria and all the tests that you that are applicable given certain conditions are satisfied. Okay, so please don't do a mistake here. Okay, and we have again a new criteria here, non-normality. So if the data is not normal, we have a few choices of test. We saw a sign test, which just looks at the differences of the signs. So it just looks at signs. And we also had the different version of Wilcoxon, the Wilcoxon sign rank test. Okay. So do you see the hierarchy of how we built this up? So we initially, like in the later part of the course, we became interested in this two group problem. To be able to understand this two group problem, we needed to understand what is independence, what's a simple random sample. We covered simple random sample, essentially what is a simple random sample? Each individual in the population has equal probability of being picked up, and picking up one particular individual does not affect picking up the probability of picking up the second individual. Okay, as simple as that. The second concept was of independence, for which we had to do some probability. And in the exercise of doing this probability, we also did some more interesting things, trying to figure out conditionality. What is the probability that one thing happens given that the other thing has happened or not? Okay, so this I need to divide. Okay. Okay. All right. So we then proceeded, and now we came up with we expanded our groups. So 3 or more groups. So all this while, what we had studied was essentially motivated by our our testing, our ability to test between two groups. Now, however, we will landed up with 3 or more groups. So we had group 1, we had group 2, we had group 3, and so on. And in such a setting, we said we can't really rely on t-testing because we can't do t-test. Why? Because it leads to inflated type 1 error. While we are at it, let me also explain what type 1 error is. Okay, so type 1 error. Okay, and the way to think about type 1 error is essentially to think about either your t distribution or your normal distribution. Okay, so I'm going to work with t. So this is, remember when we talked about p-values, we always assume that the null holds. Okay, h naught holds. So if h naught holds, this is going to be your t distribution. Okay, let's assume you're doing a t-test. Okay, This is just for the sake of explaining. It also applies if you're doing like a non-parametric test. Okay, similar logic applies if you're doing a non-parametric test. So you're working with t distribution. So you have access to t statistics. This is your observed t statistic. Okay, and you observe this, let's say here. Okay, so this TS value lies somewhere on the x-axis, and this is the corresponding density function associated with it. Okay, so what is our p-value? The p-value is the ability to be able to see a t statistic which is as extreme as this. Okay, so use colors. This is TS, and we also have a minus TS. So your H naught is non-directional. Okay, this is also important. Anytime you check a t table for or a p or any table for p-value, make sure you check the direction that this table is. Okay, in this case, my null is non-directional, so my p-value equal to the shaded area. Simple as that. Okay, nothing strange there. Probability of seeing something as extreme as my t statistic. Okay, my null is non-directional and hence it's on both sides. Okay, fine. But what's the type 1 error then? The type 1 error is determined by your level of significance. So what I said in the beginning of before I started doing this test is this, I'll call T critical, and this is your alpha. Okay, so this shaded area is alpha by 2, and this T critical is alpha by 2. So your type 1 error, what really happens? I say that a particular p-value is significant if it lies beyond my t critical values. Okay, if your t statistic is much extreme than your t critical, that means you observe, in this case, if you're on the right side of 0, you observe a higher t critical value, then you say that, the chance of observing this higher ts, okay, this ts will, let's say, lie somewhere here, then the chance of observing this ts is very small, assuming my null holds. Why? Because the density here of this curve is very small, and as such the probability of observing this is very little. So I'm saying, before I do any testing, I've claimed that if it falls in anywhere in this region of alpha by 2, which is indicated by the red color shading here, then I will say that, I do not have enough evidence. I mean, I have evidence against the null, or I have some evidence towards the null not really holding, because the probability of seeing if the null held is very small of that t statistic. Okay, so it's as good as, like, in some sense, I should not be observing a t statistic which is as extreme as this point here, or analogously somewhere this point here. Okay. Okay, and this could be any point beyond the critical value. It can be any point here, can be any point here. Okay, but imagine that the probability of observing any t statistic coming from this region is actually not zero, even if your null holds. Okay, it's still possible that your null still holds, and hence, in some sense, you're creating an error. Okay, so type 1 error is probability of rejecting H naught when it is actually true. Well, why is it actually true? Because I know that. So let's assume that the H naught actually holds. This is how I've set up my testing. And then if I'm observing the t statistic somewhere to be in this region, it's not like it's coming from the alternate. It actually is coming because the null really holds. It's just that the probability of this is small. But the way I've set up my testing, I'm saying that I can't really observe something which is as extreme, and hence I'm going to reject the null. Okay. Any questions about not being able to understand type 1 error or hypothesis testing? This is all your hypothesis testing summarized in one figure. What's the t statistic? That's something that you observe. The t critical is something which if you observe, or if anything that you observe beyond it, you're going to reject your p-value. The p-value is the shaded area, which is essentially the ability or the probability to be able to observe a t-statistic which is as extreme as what you're observing right now. And the type 1 error is the probability of rejecting H naught when it is actually true. Okay, any questions? Okay, I assume no questions, so I'll go back to what we were discussing. So we have inflated type 1 error, and we don't really want that. So we came up with a new test, which is ANOVA, okay, which has analysis of variance in its name, and it's essentially a study of the variance between between versus the within group variance, okay. And one thing that we started to focus on was the null in this case. Let me write it down here. So the null here was mu1 is equal to mu2 is equal to mu3 is equal to whatever, okay, as many number of groups you have. And your alternate is if either of this holds, that's good enough, okay. So we said that we're going to investigate this by analyzing the variance, okay, and just focus right now. So what do we focus on? We focus on how much amount of between variance you have, okay. So your F statistic is always, so B comes before within, so B is in the numerator, within is in the denominator, okay. So this is between versus within, okay. So what am I looking at? So let's try to graphically write this. So let me change the colors. So we have between and we have within. Okay, now what does the between variation look like? So the between variation essentially is summarized by your columns. Okay, so I'm looking at G1, G2, G3. This is your between, and your within is your rows. Okay, so in some sense, you're accounting for how much amount of variation do you see within the data, assuming you forget about the groups, and then you ask that the difference that I see between the groups is that high enough or not. Okay, and if this ratio FS statistic is high, we see that the chances of this holding, so Fs high implies H naught can be rejected. You can see it why, right? Because the between variance is very high, and hence the probability of this holding kind of goes down. Okay, in some sense, and correspondingly, if Fs is low, H naught may not be rejected. Okay, and essentially this was your ANOVA. Okay, so this is again a very general and overview picture. You will have access to all the formulas, but at this point, if you want to retain this course for your future self, either if you're going into research or clinical domain or any other domain where you require statistics, you might not remember. I don't remember most of the formulas, but it really helps if you understand the concept, because then, like once you graduate, or once you get out of this class, you'll always have access to the formulas wherever you go. It's more important that you really understand conceptually what is it that's kind of happening. Okay. Any questions so far? We're kind of ending towards, we're kind of nearing towards our end. And the final concept that we started to focus on was regression. Sorry, I didn't give you time to answer. Any questions? Okay, no questions, so we'll proceed. The final concept that we talked about was regression. Okay, and when we started talking about regression, we still in some sense had two groups. Okay, and so far we were asking how different are these two groups, right? So far we have been asking, whether the differences between these two groups or these three groups is different or not. How statistically different is not. Now we slightly change our paradigm. Rather than looking at the differences, we are now looking at the similarity. Okay, and the way we are quantifying the similarity is how correlated are X and Y. Okay. So we're still, in some sense, if you think about it, we are still working in the same domain. We have just kind of twisted our question. Earlier, we were asking how different are these two groups. In regression, we are asking how similar are these two groups. And in order to be able to predict similarity, we talked about how correlated X and Y are. Essentially, a high correlation implies that I can predict what value of Y I will get given I have a value of X. But correlation just is a small number. I mean, not a small number, but correlation is just simply a number. Okay, it just tells me how close are X and Y values in whatever scale they are. It doesn't really help me predict or determine how exactly Y is correlated. So in order to put that into some sort of a model, we thought of a linear model. Okay. So all these concepts of correlation and the linear model are perfectly related. It's not like a completely different concepts. And we said that let me start off with a very simple model. Let me start off with a model which has an intercept, which intercept determines how much amount of y do I have if my x is 0. And the beta 1 is my slope. Okay. Now, I think last discussion I missed out on the interpretation of beta. So this is essentially how much change do I see in y if x changes by 1 unit. Okay. Beta 1 is essentially capturing this fact that how much change do you see in y if x changes by a single unit, whatever unit that x is in. Okay. And that also tells us that beta 1 is dependent on units of x and y. The moment you change units, your beta will essentially change. Okay, so if I'm working, don't want to confuse you, but if you're working with x and y in centimeter, and if x if x is in centimeter, y is in centimeter, and now I change this to x in inch and keep y into centimeter, this beta 1 and this beta 1 will be different. Okay, very easy to see. Why? Because this unit is now different than the earlier unit, right? So if you change x by 1 unit, which is essentially changing it by 1 inch, you're changing it by a much larger quantity than in this case. Okay, so just keep that in mind. That's dependent on the units of x and y both. Okay, so how did we fix this linear model? And in order to fix this linear model, we said that, well, why should I pick up a linear model? Because, well, that's the simplest model that you can fit, and we all love it. Okay, so even you're doing complicated things, complicated data, the first thing that you would try to do is try to fit a linear model. And how did we do this? So we said that let's assume that the residuals that we have, we minimize your residuals, okay, or residual square, what you want to call it, summation of I equal to 1 to n. So you essentially minimize the summation of your residuals, and that gives you like a best fit line, which is this linear model. And each of these steps, you are essentially doing an error. So, right, I can't fix a model, which I can't fit a linear model across all these points uh, by making the line pass through all the points. Is impossible. I'll have to fit a non-linear model. Okay, what's a non-linear model? So if it's not a line, it's not linear. Okay, so this model, something like this, that's a non-linear model. Okay, nonlinear models by definition are complex, more complex than linear models. They could be a good choice for some of the problems, but are often selected only after you have established that a linear model is not a good choice of model. Okay, and one thing that kind of I think I generally see people get confused about is the proportion of variance explained. So proportion of variance explained. Okay. So what if you think about any model, what is the aim of the model? The aim of the model is to be able to get the values of y if I have values of x. So a good model should be able to capture all the variance that exists in the values of y, right? And where is this variance coming from? Well, the variance is coming because my y values are different, right? So I imagine you just have these 4 points. So you have some variance in this data, right? This is your variance in y. Now I have this linear model. So my predicted values become, these are my predicted values at these points. Okay. And you know why? Because I'm fixing the same x and I'm just getting the value of the corresponding value on the line. Okay. So variance explained essentially asks, so percent variance is how much amount of variance is explained by the red dots after having accounted for how much amount of variance is there in the blue dots. Okay, as simple as that. A good model will essentially be able to explain all the variance, and you can see when that will happen. That will happen if all the points lie perfectly along the x-axis. Okay. All right, so that was all I had to review. I hope you benefit from this overview picture. It's not very organized, but I tried to break this down into some sort of a hierarchy that we followed for this course. Okay, it's easy to connect dots back in time now because you know all these concepts. So I think when you were learning this initially for the first time, you would not be clear as to why you were learning this. But hopefully now you'll be able to connect as to why you learned what's conditionality, what's independence, why do you care about it. Okay. Any questions? Please feel free to ask me, email me. My office hours, I think tomorrow is my last office hours because actually maybe they're there for the week also. I don't know what the rule is, but feel free to email me if you have any questions. Or I'll hold my office hours next Tuesday as well, so don't worry about it. Okay. Make sure you turn in your project in time. It's due tomorrow. Okay, I'll stick around if you have any questions about R or your project, but otherwise, thank you. Thank you for sticking around, and I hope you learned something out of this course and something that will be valuable in your future as well. And sorry about these ongoing conditions. They are kind of not in our hands. But thank you for putting a good show by showing up in all the discussions. And good luck with your future if we don't meet again.
Thank you.
Thank you.
Yeah.
Thank you.